The next question of CodeChef starters 120 is count arrays. So basically in this question, let's say there is an array A, or or let's consider it as B as mentioned in the question. So let's say there is an array B with non-negative integers. So let's say there is an array B of length M with non-negative integers. Then this array is called good. B is called good if it satisfies the following conditions. If it satisfies the following conditions. So the conditions are like uh, we are given some operation. So we are allowed to perform some operation, and using that operation any number of times, we should be able to make B. We should be able to make all the elements present in B as zero. See the operations go like this. Firstly, in the operation, choose any two indices I and j, which holds the following equality: I is less than j is less than or equal to n. Right now, you need to perform the following operation. Let x be the bitwise OR of bi and bj, elements bi and bj. Then replace bi with x minus bi and bj with x minus bj. Right. So now this is the given operation that we can perform. Choose any in each operation we can choose any I and j and find out the bitwise and then set bi equal to this and bj equal to this, right? Where x is nothing but bitwise OR of bi or bj. Now using this operation any number of times, if we could make array b, if we could make all the elements present in array b zero, then we can say array b is good, right? Now the task is we are given two integers n and k. So we need to count how many arrays A are good with the following conditions. So we can array, each element in the array can have any number in the range 0 to 2 power k, 0 to less than 2 power k. So we can have any number in the range 0 to 2 power k, and A should be good. So basically we should count how many arrays are there of length n, how many arrays A of length n are there. How many arrays A of length n are there such that each element AI is in the range 0 to 2 power k, from 0, starting from 0 to 2 power k. Here 2 power k is exclusive and array A is good. So how many such array A's are there for a given n and k? And this can be very large, so we are given a mod value which is 998.244.353. So we should print the value modulo 998.244.353. So now if we look at the constraints, here test cases can be in the range 1 to 10 power 5, n can be in the range 2 to 10 power 6, and k can be in the range 0 to 10 power 6. Right? So these are the constraints. So let's see how we can solve this problem. So firstly, to solve this, let us first make some observations. So here the main observation, firstly we should figure out what type of, like how should the bit pattern look like for each number for us to make all the elements zero by applying the given operation, right? Given operations any number of times. So for that, let's think bitwise. So let's consider only a particular bit, and let's see by performing this operation how will that bit change, right? So if we perform the following operation on some I and j, where in one of the firstly if in both of these I and j numbers, b of I and b of j, if that bit is not present, so basically for I and j numbers we are considering the bit, right? And the let the array be varying only, but only thing we need is whether the bit is present or not, right? So if the bit is not present, then by the following operation we can observe that the result will also be a zero, right? In both of them, after let's say I and j, then in I dash and j dash, the result will be 0 0. That is after performing the operations, I dash and j dash changes as follows. If we have 1 and a 0, then we can observe that after performing the operation in I dash, this will become 0 and this will become 1, right? That is because in x this bit will be present, right? But in I the bit was present. Now in j the bit is not present. So we can just treat it as ones and zeros. Here the bit is present, here the bit is present, here the bit is not present. Now we need to perform subtraction. So when we do x minus I, in I dash the bit will not be present. And when we do x minus j, in j dash the bit will be present, right? Similarly holds for 0 1, it will flip the bit. Basically it will swap the bit. So 1 comes here and 0 goes here. Now if it is a 1 1, then we can observe that it becomes 0 0, right? So this is how the bit changes. For a fixed bit, if it is present in both the numbers, then it becomes 0 0. Now our aim is to remove all the bits, right? So we can see here when here performing an operation on 0 0 is useless, however it remains 0 0. 1 0 also we can say it is useless. Why? Because it won't remove a bit, it is just moving the bit. So we don't care if the bit moves or no, but our aim is to completely remove the bit, right? So performing this is also a useless operation, right? From this we can observe that it's all like we can observe that we always perform operation on two numbers if there is a bit present in both. Like we perform an operation to remove at least one bit from that number each time, right? So to remove at least, I mean to remove at least one bit from both the numbers, a bit should be present in both the numbers, right? So from this we can conclude that for every bit, this is for a single bit. So for a single bit, we can remove one by pairing it with some other one, right? So that means at a time for any bit, for a particular bit, firstly, at a time we can remove two numbers. Two, we can remove this bit from two numbers, basically. We can remove this bit from two numbers. So that means we can observe that this bit should be present even number of times among the numbers of times in the numbers, right? If we consider each number in binary form, right? So similarly, it holds for each and every bit. So for each and every bit in the range, basically for each and every bit in the range 0 to k. So 0th bit, first bit, so on till k minus 1th bit, not k, because 2 power k is exclusive, right? So for each and every bit in the range 0 to k minus 1, the bit should appear even number of times. Right? Now this observation is sufficient enough to solve the problem. We can just formulate this thing. Now the way we can formulate it is we can just consider it like a grid. So 0 represents in a number. In how many numbers is 0th bit set? Right? So let this be 0, 1, so on till n numbers. In 1, so on till n k minus 1. Right? So now here 0th bit, this represents bit, and this represents indexes. Right? So in each bit, basically considering each bit, that bit should be present even number of times. Right? So basically, if we consider 0th bit, it should be present even number of times in this column, sorry, in this row. If we consider first bit, it should be present even number of times in this. If we consider second, it should be present even number of times in this, and so on. Right? Now, let us calculate in how many ways can we uh, in how many ways can we actually put bits even number of times. So for that, what we can do is, let me fix this, right? For now, let us fix this, and in this we can put any choice, right? In all these numbers, we can have two choices. So number of numbers here are 2 power n minus 1. So in for this we have two choices, that is this bit can be present or no. In this we have two choices, it can be present or no. In this we have two choices. So on till in this bit we have two choices, right? So in total, number of choices are 2 power n minus 1. Now, after filling this, in this bit, we'll only have one choice. Why? Because let's say we filled this whole configuration with some zeros and ones pattern in 2 power n minus 1 ways. After filling that, in case if number of ones are even here, then we should forcefully put a zero only. If we put one, number of ones will become odd. Right? Or if the number of ones are odd here, then we should forcefully put one here to make it even. Right? So that is why from this we can observe that number of ways to place 0th bit even number of times in the n minus 1 numbers, in the n numbers is 2 power n minus 1, right? So now it's not necessary that we only fix this bit as the decision bit. We can fix any one bit as the deciding bit, and rest all bits we can just consider any choice among them. Basically, uh, this is just for all bits we'll have 2 power n minus 1 choices, and for the last bit we'll only have one choice, right? Into one, because this one choice depends on what we kept when we were choosing these choices, right? So so number of so placing a bit even number of times among the n numbers is 2 power n minus 1. So for a single bit it's 2 power n minus 1. Now for all bits we need to place it even number of times. So For 0th bit, the number of choices are 2 power n minus 1. For first bit, it will again be 2 power n minus 1. For the second bit, it will be 2 power n minus 1. So on till for k minus 1th bit, it will be 2 power n minus 1. Right? So in total, number of choices are 2 power n minus 1 whole power k. Right? So if we just formulate it, it just came down to a one-shot formula. Right? That is, we should just output 2 power n minus 1 whole power k, whole percentage mod. We should ensure that we mod it, and the mod result is, and the mod value is 998244353 according to the question. So this way we can solve the problem. So if we look at the time complexity, as it's just a one-shot formula, let's assume that per test case we perform binary exponentiation to find the power of 2. So per test case we can solve it in big of log. We can say it is big of log n into k in the worst case. Log base 2 of n into k. And space complexity is big of 1 space. Right? So this is per test case. So the time complexity is big of log 2 of n, big of log base 2 of n into k, and space is big of 1 per test case. And this time complexity is sufficient enough to pass in the given TL, and space is also sufficient enough to fit in the given memory. So this way we can solve the problem.